physics time. Talking about, we could call this Gravity Revisited. We have talked about gravity already this year. I don't think there's a video about it because it was before I was making the videos, but gravity. For some of us, Gravity Revisited. We're going to talk about gravity mathematically today and also conceptually. So you know about this. You've heard his name before in your life, I bet. What is it? Gravity. You know about gravity. What if you asked a kindergartner, or if I asked you maybe before you took physical science, or hopefully not if I asked you this year, what would you say gravity is? Like, what would a layman say gravity is?
The thing that holds you down.
Yeah, the thing that holds you down, right? That makes it sound like it's evil. The thing that makes it so, a kindergartner might say, the thing that makes it so something falls, right? Specifically how, though? How does the thing fall? Towards where? Let's write that down first. Yeah, gravity here on Earth attracts objects to the, as Talon said, center of Earth. That's going to give us a clue here. This, as we know, or as hopefully you can tell, is a facile definition, right? It's not exactly correct, although it is surprisingly correct, because I'm about to ask you a question. Does everything in the universe get attracted to the center of Earth? It seems like if we have one level of knowledge higher than a kindergartner, we would say, no, other objects have gravity too. We know that things are attracted to the sun. We know that things are attracted to Jupiter. But then if we have even one, this is where we're trying to get today, if we have even one more level of knowledge, we actually know that truly everything in the universe technically is attracted to the center of the Earth. It's just that it's not only attracted to the center of the Earth, right? So that's going to be our next step. Is we're going to call this universal gravitation. Let's condense what I just said and what you've read into one little brief statement. Universal gravitation could tell us, this is according to Sir Isaac Newton from the 1600s, universal gravitation tells us what? What? Summarize or synthesize. That what?
Sorry, I'm trying to write this.
Sorry, that what?
For every object attracts every other object with a force for any two objects.
Yeah, let's make that into our own words. You're right, and that's what we're trying to get to. But let's try to make it into our own words.
Every object attracts another object.
Every object, let's be a little more specific. Every object that has what?
Mass in
Yeah,
this.
every object with mass in the universe. I'm going to put in the universe because that's why we call it universal gravitation. Every object with mass in the universe attracts, oh, my marker is not having a party, attracts and is attracted to every other object. Where? Where? In the universe. In the whole universe. We think a lot of times about how if we're in outer space, we think the Earth's gravity isn't affecting us, right? You might even hear or see in movies someone say that people or objects are weightless in space. And we a lot of times, a kindergartner, maybe even much older than a kindergartner, thinks that's because they're outside of Earth's gravity somehow, right? According to this, is anything ever outside of Earth's gravity? No. So why do you feel weightless in space? Or in space? That brings us to the next thing. Here's Earth, right? This is a good Earth, you might say. When something orbits around Earth, it actually is extremely close. We think about it being really far away, but compared to the size of the Earth, something even like the International Space Station, which is really quite high up, quite a ways away from Earth, is really, compared to the size of the Earth, really quite close. It becomes clear to us in this little picture, is it still affected by Earth's gravity? Yeah, of course it is. We know that everything is, but this even very strongly is. In fact, if we did the math with our previous math, 1/2 dt squared, right, g equals 1/2 dt squared, we'd find that the gravity affecting the International Space Station is somewhere around 90 to 95% as strong as the gravity that affects us here on our surface. So it's not because it doesn't have gravity. We might say it even has 0g, right? Or we might call it microgravity. But what else is going on here? Besides just being above Earth, what else is happening with the International Space Station? We say it's in orbit. We're going to write this down. Orbit is just a fancy word for falling. It's falling in a circle. We're going to get to orbital mechanics in, I believe, the next chapter. Hold on, sorry. verify, I don't want to be wrong. No, not next. The chapter after the next one. We get to orbital mechanics in the chapter after the next one. And we'll soon find out there that this falling in a circle, that's what we call an orbit. The object has to have a certain, what we call tangential, we've heard that before, tangential speed to be considered in orbit. Because basically what's happening is the International Space Station, it's not in orbit because it's so far away from Earth that gravity isn't affecting it. It's in orbit because it's moving so fast in that direction that every single second that goes by, instead of falling down towards Earth, it does fall down towards Earth. Look at it. If it's going this way, every second that goes by, instead of being here, it's going fast enough that it's here instead. And then the same thing, it's always attracted to Earth's surface, or to Earth's core, and now it's moving this way, but instead of being just falling straight down, because it has this horizontal, this tangential speed, it moves out of the way. And so instead of falling down, it moves here. And so we get, it's circular motion, like we did 2 chapters ago, right? Does that make sense? It has a tangential speed high enough that it falls in a circle around Earth, basically because the Earth's curved, it moves away from it. Let's draw it instead like this. If the thing is moving fast enough, the classic example, and you'll see this in the video, is there's a cannonball on a mountaintop, and if the cannonball is moving fairly slowly, it just goes down, right? If it's moving a little bit faster, it'll get further along Earth. If it's moving a little bit faster, it'll move further along. And if it's moving fast enough, it'll go into orbit around Earth. So, very simply, write this down somewhere. What is it that determines if an object is in orbit? It's what? Yeah, horizontal speed causes an object to orbit. And this should be mind-blowing to you, because we a lot of times, when you think about astronauts going to the moon or to Mars, a lot of times we just think that we're getting far enough away from Earth that the gravity isn't affecting us anymore. See you later. But from this we know if we just launch an object up, the International Space Station, if we just launch it straight up, even very high, what's it going to do? If it's just going straight up, where's it attracted to? Well, technically everywhere in the universe, but it's attracted to the Earth's core. So what's going to happen? Even if it gets very far away, if it's moving straight away, it's going to do what? It's just going to fall straight back down. So what they do, this is how rocket launches actually occur. It launches a little ways, and then it turns, and it applies all of its thrust horizontally. So that just like this little cannonball, it has enough horizontal speed to be in orbit. Does that make sense? So why is it weightless? Well, where do I have that written? Why does the International Space Station feel weightless? It's the same exact reason how come you feel weightless when you've ever been in the country and some crazy driver is driving really fast over the hills and you feel like your tummy go, woo, right? Or you're on the swing on the playground, and when you get to the top, if you're going real high, for a second you feel, woo. It's the same thing. What the weightlessness is just you're feeling no acceleration due to gravity because you have some other force acting on you. Same thing with the ISS. It's moving around Earth fast enough that the gravity is not, it's not that there isn't gravity, there is gravity, 95% gravity, but there's not normal force. And we've talked about this before, but what you're really feeling when you feel your weight on the floor is the normal force of the floor pushing you back up, right? And so it's not that there's no gravity, it's that the space station is moving fast enough that the normal force is counteracted by that. So what quantities does this force of gravity depend, this universal gravitation, on what quantities does it depend? How can we make the strength of gravity, for instance, between the ISS and the planet Earth stronger? We just talked about this in the bell work. How can we make it stronger?
Increase the mass.
Increase the mass. So we know that it depends on the mass. Just of the space station, there would be a stronger gravitational pull if the space station were going around Jupiter, for instance, right? So it depends on 2 masses, mass 1 and mass 2, we call them. We're calculating this whole time. F sub g. F sub g equals mass 1 times mass 2. And what else does it depend on? Distance. It does decrease with distance, just not nearly as fast as people think. So we call it d. Sometimes we even use the letter r for radius. Doesn't really matter. But the interesting thing is that it depends on r squared. So changing what about this equation will change fg the most? Try again. The distance, right? Because it changes with the inverse square of the distance. So if we move it twice as far away, what effect does that have on f sub g? What's 2 squared? 4. 4, so it would be 1/4 as much. If we move it 3 times as far away, it'll be 1/9 as much. If we move it 5 times as far away, it'll be 1/25. So very quickly it drops off with the inverse square. So these are the quantities on which it depends. Mass 1, the mass of, for instance, the space station or this marker or your hairband or whatever, doesn't matter. The mass of some object, the mass of object 2, for us it's always going to be the mass of the Earth because we're on the Earth, and then the distance between them. What distance will we use for, like if we were going to calculate this for my podium, say, what would we use as the distance between the podium and Earth? It will be in meters, but what quantity will we use as the distance between my podium and Earth? It's on Earth, so it seems like it should be 0, right? But where do we, remember from the last chapter, where did we consider all the mass of Earth concentrated? The core. So we really, what we use for r squared when we're doing something on Earth's surface is the radius of planet Earth itself. Okay, so maybe write that down. When we're doing it for something on a planetary surface, we use the radius of the planet. But that's still not all, because if we just multiply these things, we're going to get a really quite large number. That's going to be way more than the actual, what's another way of saying F sub g? Remember? What's another way of saying the force of gravity? The object's what? Inertia? No. We had F sub g previously in another chapter. We had F sub g equals mg. We could also write, what else do we call the force of gravity acting on an object? It's
Work.
Well, W equals mg. It's what? What do we call the force of gravity acting on an object? You know it. It's
Oh, that really difficult.
weight. So this is also calculating weight. But like I say, if we multiply the mass of this podium times the mass of planet Earth and divide it by the radius of planet Earth squared, we're going to get a very large number. And so we use something called capital G, the universal gravitational constant, to make it be the right answer. G is always, capital G is always, I'm going to write this in a different color so you can see it. Capital G we call the universal gravitation constant. You might recognize part of this because we were talking about universal gravitation. And it's always equal to, you can, not only do we have, sorry I didn't mean to do that, not only do we have what it stands for, but we also have a number that it always is, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. This is what G is always equal to. So using this, we can and we will put in Taylor's mass, the mass of planet Earth, the distance Taylor is away from the planet Earth squared, multiplied by this number, and we will get a very close approximation to her weight, the force of gravity attracting planet Earth to her. This is going to link in real nicely, the last thing we're going to talk about, this is going to link in real nicely with Newton's third law, which is, what if instead of, looking at the math, if I made planet Earth mass 1 and Talon mass 2, what would be the weight of planet Earth in Talon's gravitational field? How would it compare to Talon's weight in the Earth's gravitational field? No? Think about it. If we just switch these, if we have mass 1 and mass 2 switched, it'll be the exact same. Because, when we talked about this, right? Because of Newton's third law, when you fall, when your weight is acting on planet Earth, you pull up on planet Earth with the exact same force as planet Earth pulls down on you, right? And that's shown in this too, because if we switch these two numbers, it makes absolutely no difference. The number's going to come out the same. So the force that Talon is pulling up on planet Earth is the exact same with the force Talon is being pulled on by planet Earth. How come then, we talked about this before, how come does Talon fall and planet Earth doesn't rise up to meet her? Because what? No. Because which one has more mass? Earth. And so it moves less, has a smaller acceleration. Remember, they have the same force.
So does it a little bit or no?
It technically a little bit. Nowhere, like not even the size of like an electron. It moves almost none because it has so much more mass than Earth. What we do notice is when it's like the moon in orbit also causes Earth's orbit to move because it has more close. But remember, they have the same force. Earth has a great big mass and therefore a little baby acceleration. And Talon has a little baby mass and therefore a great big acceleration, right? You remember that?
Yeah.
Same thing, except now we can calculate it using universal gravitational constant.
Mr. Kine?
Yes.
Are we watching the video today or?
Yeah.
Oh, yeah.
Aside from that, do you have any other questions about the actual stuff? We might either talk about this, yeah, we will talk about this on a video another time, but we need to talk about the tides and black holes are fun to talk about. We can do that too. Because we usually do have the chapter 12 and 13 exams together. And so we'll talk about the tides and the acceleration of Earth's gravity and black holes next time. Do you have questions about this though? Okay.